Okay, my wonderful undergrads. Today we're going to begin with lecture 2. It's a little bit behind from when I wanted it to be out in the world, but there's a lot going on here in this house today. It's a little bit chaotic. I have a 4-year-old doing 3 hours of online learning. I have somebody helping out, but sometimes I'm going to need to pause this, run away, come back, and also my husband has a series of conference calls. So finding a quiet spot in this house to film this is going to be interesting. You may see people run around in the background. Hopefully no one will be on fire. That will be a good day. I wanted to address the questions I was getting about assignment 1. Obviously, fill in the blanks, unless they're super explicit, aren't the best functioning means on our Quercus assignments and quizzes. That doesn't mean I won't use them. And in fact, in this round, you do have some fill in the blanks. But I explicitly state what you need to write. I believe they're all numerical based, and I tell you how many decimal places I want to see. So you're not going to write the units. I tell you the units. I tell you exactly what you have to write in that answer. Remember, if you have a question about the assignment, about formatting, about the way anything worked, you have TAs to reach out to. I've stated that in many spots now. It's in the syllabus, it was in the first video lecture, it was in the first slideshows, it was in the first announcement I posted, and in the second announcement I posted. So I had about 50 emails regarding that first assignment and the fill in the blanks. Obviously that meant that there was an issue. So that's not a problem. But the TAs are there to field those questions as well. We did put an announcement out. I did get a lot of questions after putting the announcement out. I would have assumed that saying we will fix those marks in the Excel sheet at the end of the term would have implied that that means we're going to give you the marks. I'm certainly not going to take more marks away. Otherwise, what are we fixing? But I'll try to be, as one student mentioned, be more explicit. So I will try to be more explicit with all of you. Today we're going to move on to loads. There's not a lot of math in this, but there is a little bit of math, and you're going to have a little bit that you have to do. Remember, with the assignment, you have time. Take it slow, take a look at it. Don't rush and put your answers in. Think about it for a while. Make sure you have in there what you want. Read the questions carefully. I will try to be very explicit about what you need to do. I want you guys to get high marks. I don't want to have to answer 50 emails. So I am going to try to do whatever I absolutely can to make sure you have all the information you need to do this correctly. So today's lecture, we're going to go through loads, what those main load cases are. We're going to talk about how we combine them up, because if you remember, I briefly addressed that we do ultimate limit states design in our courses, or in our design code in Canada. So part of that is that we put different factors on different loads. We increase each load by different amounts depending on the type of load it is. So I will go through what those load combinations look like. What's interesting about that is that changed since last year. So all of the examples have been reworked because the load combinations are different this year in the companion load component. So I've tried to be very careful. Hopefully there's no typos, but we do have TAs working through that. If we do find a small mathematical typo, I will update it and fix it in the slideshow, and I'll try to put an announcement out. And then we're going to talk about tributary area or tributary width, or what region of our building puts load on a specific item. And part of that leads into how we read basic drawings. So this was the other big thing of why this lecture is a little bit late today. For years, I had a set of basic drawings that I referenced when we talked about what basic drawings look like. And it was the same building, trying to show the most common things, which it's actually really surprising to have a set of... Here, hold on a second. Sorry, I'm back. My son needed to be able to communicate with his class for a few minutes. They keep them on mute, and every now and then one of us, me or the other helper, has to go turn the screen or the microphone on so that he can talk to the students. She had it, but I just needed to go double check. So these basic drawings that had been around for, well, I got them from my predecessor teaching this course, or not this course, but a component of the graduate course. And then they got it from their predecessor. So they had been around for 20 to 30 years. They were an old formatting type. They used some nomenclature we don't really use anymore. So I set out to update them, which should have been a simple task, except once I did that, I wanted to design it. I wanted to make it right, because then we could use it throughout the term as a kind of basic reference building for some of our calculations. That turned into a whole new task. Basically, I designed the same building twice in steel and concrete from top to bottom. I didn't get through all of the sections, so you're not going to see the sections of the buildings, but that is my ultimate goal, to have that completed. But just to give you a sense, that's the sort of project that typically, if somebody was hiring me to do, I would have had 4 weeks worth of work in that. And I had about a week and a half to jam it in, as well as prepare all of the other stuff for these courses. So there was a lot of very long, very late nights trying to create those for you, but we have a new reference set of basic drawings to take a look at. We're going to go through them at the end, but you also have a PDF of them that you can download. I have some screen captures of it in this presentation that we'll look at, but I might also open up the actual PDF of it so that we can kind of zoom in and talk about things a little bit. And there's two ways I've written notes on that. Some of it is in a faint writing. Those are things that wouldn't have actually been in the drawings, but they're kind of notes and explanations for you to kind of get an idea of what's going on in it. Sorry, things keep coming to me that I wanted to talk to you about. The other thing is that I did get one really good question about last week's lecture and assignments and quizzes. And that had to deal with serviceability. Somebody said they didn't know which serviceability requirement to put in the answers because I talked about two of them. Now, in the question, I did explicitly state which one to look at, but I didn't explain that those two things, so if we have a roof with finishes that can be easily damaged, we actually have two criteria we look at. We look at dead and snow together. Actually, if there was live, we might have three criteria we look at. Then dead and live, and then before, snow by itself and live by itself. And the reason it's not apparent which one governs is that those loads can be different amounts. And then we combine them with different load combinations that we're going to talk about this week. So the answer is you don't know what one governs until you figure out what the actual deflections are. So you can't know which of those serviceability criteria is the ultimate ones because they apply to different things. You can't compare apples and apples. What you have there is an apples, an oranges, bananas, and pineapples list. And we need to figure out how many apples, bananas, oranges, pineapples, I think that was all of them, that we actually have. So there is no one answer for the serviceability criteria. Technically, we don't for the strength stuff either, but usually that works out pretty apparently which one we're looking for. Again, I apologize for the noise in the background. So let's start with the lecture. We're going to jump in to the types of loads a building sees. Okay, so the first one is live loads. So I'm going to try to give an explanation about what these loads are. Live loads usually are all the people in the building. So you and me sitting in my house, I'm a live load in my building. My kids dancing to a video in the other room, they're live load in that room. But it's more than just that. Live loads are also the chairs and the tables. Anything that's not nailed down to the floor is considered a live load. Even some things that are nailed down, but they have to be really, really fixed down to not be considered part of the live load. Even partitions, depending on how you read the code, so that's walls that aren't structural, can be considered part of the live load. We break live load down into different kind of categories. We'll talk about assembly loads, which means lots of people can gather in it. Offices, libraries, corridors, residential. There's actually a whole list of live loads. If you go into the PDF Helpful Downloads module, you will find a live load table. That is from the National Building Code of Canada, and that is the loads that we have to use depending on what type of building it is. So once we know we are designing a museum, we would open that up and say, okay, here's what the live load is that we have to use when we're designing a museum. So before we actually talk about what these loads are, it might be helpful to talk about what they look like and what they mean. So an assembly area is listed as 4.8 kPa. What's a kPa? That doesn't mean a whole lot to you. Well, kPa is also how many kilonewtons per meter squared something is. If you remember last lecture, I showed you what most of those basic units are. So kPa is kilonewtons per meter squared. So how many kilonewtons we can cram into 1 meter squared. So if we said that Arnold, I tried to find a modern day kind of famous person, man or woman, that weighs about 225 pounds. It was kind of hard. Arnold is pretty much the closest. He's 229, but we're going to round that down to the 225, or he was in the day. So we're going to round him to 225 pounds, which means Arnold is about 1 kilonewton, because if you remember, 1 kilonewton was about 225 pounds. So if Arnold is 1 kilonewton, and we have 4 kPa, or 4.8 kilonewtons per meter squared, we need 4.8 Arnolds crammed into that 1 meter by 1 meter squared. What I used to do when I would teach up in front of all the students, before I showed this slide, before class, I would tape out on the floor a 1 meter by 1 meter square, and I would call up some students to stand in the square with me. Now, 4.8 being 4.8 kilonewtons per meter squared, most people don't weigh 225 pounds. You definitely have people that weigh 225 pounds, but the average group standing in that square would probably be, somewhere between 120 and 200 pounds. So that means that's not enough. 4.8 people isn't enough to represent our 4.8 kPa. And I think I show that a little bit later on. So we'll come back to that in just a few minutes. I kind of hate this slide because I'm not a fan of super scrawny supermodels. Back in the day, I was a super scrawny person. I definitely was not a supermodel. And I was often kind of made fun of for my weight. So I try to be very careful about kind of weight categorizing anybody. But this model happened to very publicly weigh about 112 pounds, which is about half of a kilonewton. So we're going to use her as half of a kPa, or half of 1 kilonewton. So that means if we needed to represent 4.8 kPa using her, we would need 9.6 of her. So 4.8 kPa is the equivalent of 9.6 of her standing in a 1 meter by 1 meter square. You can imagine that starts to be pretty uncomfortable. Maybe they're stacked on each other's shoulders, I don't know. But it starts to be a very uncomfortable space, as anybody who's ever stood on a subway platform pre-COVID would know. It'll be interesting to see if we start seeing changes to codes and load requirements as a direct implication of COVID. But that would be several years down the road, and there would have to be some serious long-term kind of lasting implications of gathering spaces to see that start to happen. So 4.8 kPa, if you deal in imperial, you'd often refer to that as 100 pounds per square foot, or PSF. When my husband and I talk about loading, we'll bounce ideas off of each other, and he'll be like, oh, it's about 40 PSF. And I'm like, okay, old man, okay, boomer, which sadly, I'm pretty close to myself. But we won't get into that, nor will any of you make fun of me for that. Don't you dare write that in any emails. The question is 4.8 kPa comfortable? And it's not really. We don't like to do it unless we're in very specific circumstances. We tolerate it on the subway, probably muttering under our breath the entire time. We tolerate it in gatherings where the whole point is to be jammed in together. So you can imagine those ones like a dance floor or a sporting event where we really love that sensation. It's a sense of bonding. But we can get that 4.8 kPa kind of jammed in together. But you usually leave those feeling hot and sweaty and uncomfortable, and it resonates with us. It's a kind of thing that stands out. So here's an image of probably something that would have been about 4.8 kPa. I thought I had found an image of the Raptors winning previously, kind of all jammed in, because that definitely was 4.8 kPa over a large majority of our town, or the Toronto. I guess I'm in Port Hope right now. So here's another example of 4.8 kPa, where we would have them in bleachers, stadiums, and grandstands. Interestingly enough, if we have fixed seats, that 4.8 kPa can be 2.4 kPa. The idea being there is that if you have lots of seats, and we're talking like really fastened to the floor, not ones that you glue down and move around, or furniture that's really heavy. This is fixed seating. So a classroom with movable tables would not be that, except it falls under its own category, so we're not going to use that as an example. But if you're in a church, for example, and it has fixed seats, you could say that it was only 2.4 kPa, because it's hard to fit that many people in, because the seat sticks out. It's hard to kind of get that amount of people jammed in there. Dining halls, if they're under 100 square meters, you can use 2.4 kPa. If it's over 100 square meters, you have to use 4.8 kPa. If anyone's been to a wedding where it serves as the dinner and dance area, you've probably been there where they say, go outside for a few minutes, come back, and that dining hall has turned into this. So that's why a large dining hall that can have a big enough crowd, we have to assume that there probably will be dancing. Let there be dancing at the end of the night. And so for those, we definitely need to assume we could have 4.8 kPa. Then we have our non-assembly category of things. So an office building would be a great example of a non-assembly building. For office buildings, we say that no matter what, the ground floor is probably going to be an assembly area. If you've ever been in any of the major buildings downtown Toronto, you know that they have big lofty ceilings, nice open spaces, and you've probably seen Christmas parties happening in the foyers of those. Even at Daniel's, in the main areas, we have large gatherings, even though it's a school building. So it's very easy in those big kind of showy spaces to have assembly areas created in those. So the ground floor would be 4.8 kPa, and the upper floors would be 2.4 kPa. So you're probably wondering, what does it matter about the ground floor? That's just the ground. It's just sitting on the ground. That's true if we don't have a basement in our building, but most of those buildings actually have a big, massive basement. Anybody who's walked on the path underground knows that those underground spaces are not only there, they're bigger often than the footprint of the building. A lot of the setbacks for properties are about the above spaces. So how much space there is around the building above grade. Often, and you have to be double certain and check this with your building department, you can often build right to the property lines below grade. So that means that this space right here has a big impact on how we design this floor. Residential spaces are 1.9 kPa. When I started teaching this course 7 years ago, the residential loads were broken into two categories. We had 1.4 in bedrooms and 1.9 in everywhere else. I don't know what happened in what particular bedroom, but they decided that that was not good enough, and they changed the standard residential loading to 1.9 kPa, no matter where you are in the residence. Vehicles have very specific loadings, and they're surprisingly light. So a car is 2.4 kPa. You're probably thinking, that makes no sense. People have 4.8 kPa. The idea is there that is, in spite of the fact that a car is very, very, very heavy, it's spread out over a relatively large area. So that weight is kind of spread out over the whole footprint of the car, acknowledging that it comes down on the tire points, but that is a separate calculation that we think about very explicitly when we're doing punching shear. That's kind of beyond the scope of this class. So we're talking about the overall load on the floor area, not specific tiny loads on a very small footprint. So the car over the building for its area would be 2.4 kPa. So a parking garage, if it's just holding cars, would be 2.4 kPa. But we know that often buses and light trucks might go into parking garages if they have high enough ceilings. For those ones, we would say 6 kPa because we've got a bit of extra height there. The big one is big trucks, and that includes fire trucks, which are very, very, very heavy and dense relative to their footprint, especially if maybe they have a small water reserve or other gear on them. I know that they often use the pump, but the pump itself is very heavy. For those, we use 12.0 kPa. This has a really big impact on these buildings here. So there's two things. If this is our below grade space and a fire truck can park right here, well, that's got to have 12 kPa on this portion of that design. Also, if we have a fire truck parked right here, the soil here wants to push down, and as I talked about last week, it then wants to kind of fall into that hole. We're going to talk about that a little bit later when we talk about soil loads as well. So that's the majority of what I wanted to talk about with live loads. Let's move into dead loads. So there's kind of two components of how we think about dead loads. There's self-weight and superimpose. For most of our calculations, we're going to jam those together and just talk about the dead loads. So don't get too fussed if you don't see a breakout of self-weight and superimposed loads. I want you to understand that they exist and what they are, but we're going to work as kind of a whole entity of dead loads for the majority of this course. So self-weight is the weight of the structure. So our steel beams have a weight, our concrete floor has a weight, and depending on the type of material we use, that weight can relatively be quite high. Sorry, I have the hiccups a little bit. Concrete floors can be very, very, very heavy, so we have to leave a big allowance for their self-weight. Then we have superimposed loads. So that's all of the dead loads that go on top of it. That is less about what the engineer, the reason we often break it out is because the engineer is usually controlling how much of that structural material we need. So we need to go back, we have to do the design, see if it works. If we need more, then we have to make sure we update the self-weight in our design. So we often pull it out sometimes in our calculations so that we can update it easily as we do our math. Superimposed loads often are all about what the architect picks. There's back and forth and communication, and the architect and the engineer looks up what those are. But it's often because of what the architect is picking in the building. So you're putting carpet on your floor, an engineer will look up what weight allowance we use for carpet. You're putting ceramic tiles on your floor, we'll look up how much weight we need to allow for a certain amount of ceramic tile. And there's a whole list, again, like the live loads, you can go in to your module for downloads and you will find a PDF that is all about dead loads. And there's a list there. There's some from a few different books, but I'm primarily going to use the Steel Code version, which I believe is the very first page. We're going to use it. We're going to take a look at it here in a few minutes as well. Those are something we can look up directly from the PDF. There's some interesting kind of communication about it. They kind of group things in different orders. You're going to have questions about that on your assignment. So stop, read, I give you hints. I basically tell you where it is on the page. So there's no excuses if you look in the wrong spot. Because sometimes people get confused about the 3 different spots concrete is, because they're very specific things that we're talking about. We're going to do a few examples. Remember that I will post a separate video where I post specifically about examples as I work them out by hand for you. So here is the sheet that I was talking about. You have this in your download. So you should know how to look these up. You can see here, I'm gonna have to lean forward, so I apologize for getting closer to the screen. But you can see here, steel decks. Steel deck, 38 millimeters deep up to 0.91 millimeters thick. This is the norm. Unless I tell you otherwise, this is what we're talking about. 38 millimeters deep, 0.91 millimeters thick, or 0.1 kPa for our metal deck. So if I say, what is 38 metal deck? That is what I'm talking about. I know that there will be people that say, you didn't tell us what steel deck, and I'm going to say, you did not watch this video. So it's been here explicitly. Everybody can kind of come back, watch this video, and know exactly what we're talking about. If I said something else, if I actually wrote out 1.22 millimeters thick or 1.52 millimeters thick, you would know you would use the other element. I don't think I'm going to do that. It's always going to be 0.1 kPa. Let's see what else is on here. Concrete per 100 millimeters thick. Remember, 100 millimeters is about 4 inches. So if we say 4 inches, we're talking about 100 millimeters of concrete. We have it broken out into different weights. There's super light density, slag aggregate, and ND. ND is normal density. So I don't think I need to explain that normal is what we normally do. So if I say concrete, 4 inches of concrete or 10 inches of concrete, I am talking about this right here, which is 2.31 kPa. So that means that for every meter by meter, if it is 4 inches thick, it weighs 2.31 kPa. If you have 8 inches of concrete, you're gonna have to figure out how much that is. You're gonna have to do a ratio and figure out how much concrete that is. We'll do that in one of the examples we do kind of going forward. We have different types of roofing here. Gypsum wallboard, often written as GWB, is drywall. So if you hear us talk about drywall, and you're gonna have to talk about that, you're gonna talk about that in all of your courses or a bunch of your courses across the term, I'm sure. It's written out here. It's written in more than one spot. It's written down here in walls and cladding as well as in roofing, because that's often what we put on the underside of the ceiling. You can actually see it here on the underside of my ceiling. We've got some, actually this might be lath and plaster, whole other thing, but often we use gypsum wallboard as another nomenclature for drywall. We have plywood, we have wood joists here. So these are calling up 2x8s, 2x10s, and 2x12s at 16 inches on center, or 400 millimeters on center. Then down here we have deck slabs. Deck slabs are an assembly of concrete on metal deck. We're going to talk about all of these again more later, but the most standard thing is 38 millimeter deck with 65 millimeters of normal density concrete on top of it. So you do not have to go figure out how much concrete that means. I'm just going to grab my pen here. I wonder if it will let me write on my screen. I know I'm still talking even though you can't see me, but I have a very fancy, very expensive monitor that lets me write on my screen. Anyway, I'd have to dig out my pen. We'll come up with a way to look at this more later. But this one right here, 38 millimeter deck, 65 millimeter normal density concrete, that is going to be the one we use again and again and again and again and again, is 1.95 kPa. So we're going to go through this example here right now. I'm not going to break off and do this by hand because I think we can talk through it in a pretty simple way. So the first one is 4-ply with gravel. Now we're looking at the dead loads for a roof example. So 4-ply with gravel probably means we're talking about roofing of some sort. We can come over here, roofing right here, 4-ply asphalt and gravel. Looks like it's 0.32 kPa. So we would write down 0.32 kPa right here. 6 inches of rigid insulation. So let's come back here in insulation. We've got 100 millimeters per 100 millimeters thick of insulation. We've actually got 2 here. We've got glass fiber rigid and urethane rigid foam. I'm just going to jump through and take a look here. If I was giving you this as a question, I would be much more explicit about which type of insulation we're talking about. But we're doing this one with glass fiber rigid, and we have 6 inches of the glass fiber rigid, which is per 100 millimeters is 0.07 kPa. But we have 6 inches of it. So 6 times 25.4 is 152.4, and that's per millimeter. So let's divide that by 100, which gives us 1.524 times 0.07. We're going to get 0.1 kPa of rigid insulation that we need to account for. So 6 inches of rigid insulation is going to be 0.1 kPa. 38 metal deck. Well, they haven't said anything about any weird types of metal deck. And I told you that if we're talking about a 38 millimeter steel deck, we're talking about this one that is 0.91 millimeters thick, or 0.1 kPa. Open web steel joists. Now this one, that is self-weight of the structure. You're not going to know that one. You can't know what that one is. This is something that I would give you something to assume. I would give you a really good example or a standard that we would use as a placeholder to do our design. And then once we see if our design works, we'll check and see if it's within that allowance of what we gave ourselves for a self-weight of the structure. Same thing with the steel. So we'll leave those 2 blank, and I'll come back in the next slide and I'll show you what those are. So we'll finish looking up the ones that you guys can look up and come back to the open web steel joist and the steel. So the next one is mech-elec, or the mechanical and electrical. If we come here into ceilings, so that's everything that kind of hangs from the underside of our floor or our roof. There is something here that is ducts, pipes, wiring allowance. Ducts and pipes, that's mechanical. Wiring allowance, that's electrical. Average condition, 0.25 kPa. So pretty much standard on any structural drawings of any firm you're going to see in Canada. They are going to leave a 0.25 kPa mechanical electrical allowance for their floor or roof assembly. So we'll put 0.25 here for mech-elec. The last one is suspended. So suspended is that kind of crappy, ugly tile ceiling that you see hung down on T-bars with those big kind of acoustic panels. Usually 60% of the time I'm teaching this course, we're in a classroom with those ceilings. But you can see here, under ceilings, tiled ceiling and suspension system with fixtures, average 0.2 kPa. So that is our suspended ceiling allowance. I'd often try to be very explicit, but you've heard me say it here. That is our suspended ceiling. So that standard kind of, if you've been in a Walmart or a store, they often now start to leave their ceilings exposed, but you've been in those stores, you've probably seen them kind of gross with most people, water soaked through them. But that tiled ceiling or suspended ceiling is pretty standard. So we looked up our weights for all of them except our open web steel joists and our steel, which I've told you I'm going to give you. So we had looked up the 0.32 kPa for the 4-ply with gravel. We had to do a little bit of math because it only gave us 0.07 kPa for 4 inches of rigid insulation, and we have 6 inches of rigid insulation. So we need to multiply it by 1.5, and we get 10 kPa, or 0.1 kPa, sorry. 38 metal deck, we looked up. We know that we'll use 0.1 kPa for that. Open web steel joists, a good allowance is 0.15 kPa. I'm telling you here, unless I tell you something explicitly in a different question. I would always give you that. Unless I said, what's a really good example, and then I might give you a few values as an option. But 0.15 kPa is a really good allowance for an open web steel joist load. Steel, so that's the steel beams, the steel columns, everything that we kind of throw in there that would impact that load. A good assumption is 0.2 kPa. So the thing I often get asked here is, but my open web steel joists are discrete and my steel beams are discrete. How can we apply that as a per meter by per meter area? What we assume here in our design is that we take all that steel, it's not literally what we do, but the way we think about it is we take all that steel, put it in a blender, turn it into a spread, and spread it out all over the floor. So we're basically assuming the weight of the steel is distributed evenly everywhere on the floor. We know that's not true. In high load or very specific cases with very large members, we might not follow that approach, but most of the time it's a pretty good way to do our calculations. So the problem there is we don't want to say things like our metal deck are holding up our open web steel joists and our steel, because our roofing sits on our metal deck, which spans to our open web steel joists. So the open web steel joists are going to support the deck. The deck does not support the open web steel joists. So it seems a little weird to tell the deck when we design it that it has to include a weight for open web steel joists. So there we'll often break it down into subcategories. We might say for everything that's deck, that supports that the deck supports will add up. So for example, the deck has its own self-weight. It also has the rigid insulation sitting on top of it. You see that this list of things is usually written in order that they appear working top down. So our deck has its self-weight, it supports the rigid insulation, and then on top of that would be our 4-ply asphalt with gravel roofing. So the metal deck, when we design it, would have 0.1, 0.1, and 0.32 kPa on it. So the deck would only actually support 0.52 kPa. But then the open web steel joists would have the weight of the deck and everything the deck is supporting on top of it. So the open web steel joists are not supporting the steel though. The open web steel joists are spanning to the steel. So now we have to think about what weight does the open web steel joist support. So this is where you don't know this, and this is something that I'm going to tell you, that often we hang things from our open web steel joists. So the open web steel joist wouldn't support the steel because the steel supports the open web steel joists. But the open web steel joists would probably have mechanical and electrical hanging from it and that suspended ceiling hanging from it. So in that respect, the only thing the open web steel joists wouldn't support would be the weight of the steel itself, or 1.12 kPa. This is slightly less obvious to you. I would be very explicit about a breakdown there, but I just want to show you that as we kind of go down through the design of the elements, we keep adding things to it, which means we're adding weight to the subsequent elements. So as things start to support other things, their responsibility and their weight grows. I can think of 100 examples, and we're going to talk about one of them later in the lecture, so I'll stop right there. Before we go on to the next few items, I want to talk about importance factors. This is one of the things that the majority of the students go rogue, and I can't understand it. I'm hoping maybe where we have videos posted, it'll happen less often, but most buildings are normal. If you don't hear anything, if you know nothing else, your building is normal. You don't need to go out of your way to figure something out. But what does this mean? Why would we say some buildings are more important than others? The thought here is that A low importance building is something that if it did fall down, no one's going to be around, no one's going to get hurt. There's certainly monetary loss, which is unfortunate, but no life is at risk. So no, it's unlikely that anyone would have a problem there in that. So these would be low human occupancy buildings where it's shown that a collapse is not likely to cause injury or other serious consequences. So that would be something like maybe a barn that you just have storage in, there's your tractor trailers in. Yeah, sure, you go into it to drive your tractor out, but you're not in there very often, and you're not there, you're rarely going to be there in the event of a high-risk event. So this would be a big windstorm or a big snowstorm. You're probably not out puttering around your garage or your barn. Your garage would be a normal building because it's attached to your house and you use it all the time. I'm talking about that kind of remote building that's unlikely to be used. I rarely use the low importance factor. And if everything else works as normal, even if it could be qualified as a low importance, I still design it as normal. Because why? The cost is nominal. I might use low importance if it meets all those criteria, and also we're having a hard time getting an item or an element to work in the design. That would be the only time I might use a low importance factor. Otherwise, your building's normal. It means that unless it's low, high importance, or post-disaster, you're going to use normal. High importance buildings. These are buildings that after a big event or a disaster, we would use it for shelter. This does not mean it has to work the way it was originally intended after a disaster. If you have an arena and a hurricane hits, you are not going to assume they're going to want to play hockey in that arena right after the big natural disaster. People are going to want to go there, have a safe spot to be, set up cots, have emergency first aid. This is going to be a spot where it doesn't have to function the way it used to. Sad story though, sometimes some arenas, if they are owned by a city or in a remote region, they might sometimes be designated as post-disaster if they have to be used as a temporary morgue in a post-disaster event. I always used to say this kind of as an interesting side note, but it's a thing we've seen in places like Italy, where they had such a high death toll due to COVID that they needed cold places to store bodies. So it is a unique category that normally it might an arena would just be high importance. So that's something you'd need to check if it might possibly need to be post-disaster. But normally we're talking about buildings that people need to gather in after a disaster. A post-disaster building is one that needs to function as intended after that disaster. So this would be your hospitals, your police stations, your fire stations, your ambulance dispatches, also communication hubs. We rely on communication so much now, so that would be like internet provider stations, radio stations might be considered post-disaster. Because they need to keep functioning as intended after that disaster to get information out so people can stay safe during and after the disaster. Sometimes my kids may end up running in. I can hear Jackie kind of trying to keep them back right now. I apologize. They're pretty adorable, not gonna lie. If they show up, you might just have to ooh and ah appropriately. I'll assume you're all oohing and ahhing appropriately when the time comes. So what do these importance factors look like? We break our design up into two things. We have strength and we have serviceability. And I talked about those two things last term. And we even, last lecture. I even talked about serviceability having different criteria, whether it's dead and live or live by itself. And I said we're going to talk more about that later in the term. One of the places we're going to talk about that is how we apply our importance factors. So if we're talking about strength design or our ULS or ultimate limit states design within that, we're talking about these factors right here. So for a regular building, our importance factors are 1. I said it was normal. It means we just keep on doing the same old thing. If it's high importance, we will increase it wind and snow by 1.15 and seismic by 1.3. So a 30% premium on our structure for seismic loads. the part that is supporting seismic loads. Do you need any help, Jackie? Do you have it? Can you get logged in? Do you need some help? Okay, I will pause this and we'll start coming back in just a second. Okay, so I'm back. My son is back logged on, and my other one is, I don't know, he might show up. I did learn how to splice these videos together so I don't have to post multiple small ones. It will be merged into one. You're watching it, so you already know that, but I was very excited. So I was talking about the strength elements having their importance factor applied. Post-disaster, you can see, ends up having a really big premium put on it. Seismic, 1.5 times, so 50% more seismic load gets applied to the building, to post-disaster buildings than a regular building. I often joke that we want it to survive the apocalypse. It's less of a joke now. 2020 has been a bit of a MFer, so we will hopefully not have to actually employ that, but you can see that we apply different strength factors, importance factors, depending on the type of building it is. Deflection pretty much stays the same no matter what, because if you remember, strength or serviceability is all about preservation of finishes and people's comfort. If that floor moves a little bit more during an earthquake, you're not going to care that much. If your ceiling finishes crack during a massive disaster, during a big earthquake or a hurricane, you're going to be okay with the fact that your drywall cracked because everybody got out alive. So you can see here that for wind, for serviceability and deflection, for low, regular, high, or post-disaster, we apply a 0.75 importance factor. For snow, no matter what, we apply a 0.9 serviceability factor, or a importance factor for serviceability. And seismic isn't applicable. We don't really do serviceability checks the same way for seismic loads. And if you remember, well, I'm going to show you later what the load combinations are for seismic, and you're going to see that they're pretty much 1 compared to the other loads. So you'll see why that serviceability check doesn't really matter quite as much. We would do the same load case. So if I tell you that you've been given a load and you need to do a serviceability check, you would need to apply this serviceability importance factor to it. Hint, hint, you definitely have a question like that coming through to you. I can't remember if it's in the assignment or quiz, but one of them definitely has that. I think I explicitly say it in the question. Reminder, hot tip, this doesn't have the serviceability importance factor applied. So for that, for snow, you would want to apply the 0.9 to the load. So let's keep going. So let's take a look at one of our load cases. So those were our importance factors. Let's actually take a look at a load type. I've now broken these out into, we've moved on to our climatic data load types, or loads that are dependent on statistics in your region. So what we designed for in this is, some of it is actually, we have a few components to it. We have where you are in Canada, where locally within your region, are there any kind of quirks because of where you are locally? What about the local terrain? What about any special local conditions? And what about the size of your building? So we kind of start at the higher and work down. So snow load is our importance factor for snow load times. Now, pay attention to your brackets. I expect you guys to know order of operations with parentheses. I'm not going to go back and teach that, but if you're confused, stop and take a breath and look that up. Most calculators will do it if you apply the brackets as I've shown them here. If not, if you apply these in order, you're not going to get your importance factor applied to this number over here. So make sure you follow the brackets properly. So it's the importance factor for snow applied to the entire equation, which is SS, or a snow load that you're going to look up in a table and you will find that I've uploaded climatic data, and one of the lines in it is snow, or SS. So SS is our 1 in 50 ground snow load. So what we're saying there is in 50 years, the worst storm we're likely to see is this much snow, or this much kPa of snow. Obviously, statistics are only statistics. It doesn't mean it is the absolute. So you could have 2 1 in 50 year storms in the same year. It's not impossible. We have had some major storms in Toronto in the past. Well, anybody who lives in Buffalo, if you lived in the wrong half of Buffalo a few years ago, I think it was 2014, you were walloped with snow. That was well beyond a 1 in 50 year snowstorm. It was more like a 1 in 100, maybe even a 1 in 150 year snowstorm in those local regions where you got so much snow. So we start with the 1 in 50 year snow load, and then we do some things with it. And now that's saying on the ground. We also add a little bit over here for rain. We acknowledge that when it snows, you can have rain just after or kind of mixed in with it, and the snow kind of acts like a big sponge. Instead of that rain just falling off like it normally would or going right down the drain, it gets stuck in that big mass of snow. So we add sometimes I call it the wetness to the snow. So we look up SS and SR in our climatic data, and I'll show you an example of that. Then we add some factors. We have some factors that we need to add to this. So we have CB, CW, CS, and CA. These are all things that are dependent on the specifics of our building or where our exact building is in terrain. So these two things are where we are globally, or nationally, if you want to call it that way. CB is the basic snow load factor. 0.8 for Part 4 buildings. 0.6 for Part 9 buildings. We are not doing Part 9 buildings in this course. This is another thing that I say this during the lecture, and I can always tell who does not show up to my lectures. It's a little bit different. I'm hoping the video recordings are going to change this, because inevitably somebody applies 0.6 as the basic snow load factor. I'm always baffled because the only place they can get that number is right here, where it literally says in the same slide, do not use this in this course. So for us, CB is 0.8. It's just 0.8. We're going to use it as 0.8. CB is saying that our snow is coming down on top of our building. And most buildings are small enough that when that snow comes down, some of it kind of comes off the building and hits the ground. So on the ground, it can only go to more ground. On the roof of a building, some of it can get down to the ground. It's beyond the scope of this course, but on really, really, really large buildings, that CB factor might change and go up to 1. So somewhere between 0.8 and 1. I've done a few large, low arenas. So usually more the suburban or rural style arenas where they have all kinds of land space and it can spread out over a big terrain, where you can imagine the middle of the roof, there's nowhere for the snow to go but other roofs. So there our CB might go up. But for us, don't worry about it. You're going to use 0.8. CW is the exposure factor. This is saying that wind will blow snow off the roof. You're going to use 1. Don't use anything else but 1 unless I tell you something super explicit to do. It is really hard to have any other criteria. So you can see there's 0.75 of exposed to wind on all sides. The clause goes further in that and says nothing taller than the building within a 1 kilometer radius. That is almost impossible to hit whether you're rural or suburban. There's almost always something, whether it's a tree or a building, somewhere within a kilometer of your building. So that would only happen kind of like out in the middle of the prairies would you get that. So not normal here. 1 is our typical. Hi, Duncan. 0.5 is if it's exposed to wind on all sides above the tree line. There it's slightly more probable. You could have something remote where you could imagine it would be very easy for wind to blow the snow off the top of the roof. CS is our slope factor. Flat roof, 1. That does not mean no slope, the factor is 0. If you do that, you will have no snow on your roof or almost no snow on your roof. That's not what it's saying. Flat roof, factor is 1. We have all our snow there. As it starts to pitch and we get slope, we start to get sliding. But we don't even say they're sliding at all until we're at about 30%. So from 0 to 30%, we still use a CS of 1. At 30%, we start to apply a CS factor, and it is linear all the way up to 70 degrees, and then at 70 degrees, we say, oh, the snow slides off. That changes a bit if it's slippery roofs, but it's hard to get a slippery roof. That's an unusual kind of condition. So for us, don't even worry about it if you have below 30 degrees slope. This always begs the question, and I always see it, people making this bold move that they're going to make a super steep roof to get rid of snow. That makes sense in places that we have high snow. Toronto has snow, but it isn't as high as some other regions. We end up with about, in Toronto, 1.12 kPa of snow. We're going to do that calculation, don't worry about it. 1.12 kPa of snow. Places like Ottawa are somewhere in the region of 2 or higher. In Toronto, it's almost not worth trying to get rid of the snow. We would have then a live load that would start to weigh in on that. It's just not worth trying to design to get rid of the snow. If you have, for other reasons, a sloped roof in Toronto, you might as well take advantage of it, but don't go out of your way to design for that. Where it is smart to do is in places where we have snow loads like 4 kPa. And you've seen kind of a whole architecture type in like Moscow where they have those onion-style buildings. That was actually the principle there, that they had such high snow loads that they designed them to shed the snow right off the roof. So for us, usually 0.8 for a basic snow load factor, so CB, usually 1 for CW, and usually 1 for CS. There's one factor left, and for you, we'll get to that one in a second. So we'll get to CA in just a second. So the climatic data we look up. Here's a little kind of screen capture of a region of the climatic data that you guys have. You can download this. You should have it, maybe even have it open on the screen beside you. I've pulled out here Toronto. So we can see Etobicoke, North York, Toronto, and Scarborough. Over here, we have snow load, KPA 150. That's saying we're talking about our 1 in 50 year snowfall event, or the big storm we're likely to see every 50 years. And here we have SS values. You can see for Toronto City Hall, it's 0.9. And then in North York and Scarborough, it's 1.2. And then we have SR, which is the associated rain load, which is 0.4 that gets added into that. So these we look up. These are something that we go to the code, we know where our building's being built, and we go and look them up. We talked about the other factors. Hi, Duncan. And then we have our accumulated snow factor, or our CA, accumulation factor. You guys are going to use 1. You guys are not going to have to design this. It's beyond the scope of this course, but I want you to understand why it exists. Here's our snowfall. That seems relatively normal. But look, we've got this high building here, a mechanical unit here, and a parapet here. When wind blows and moves snow around on a roof, some of this snow will fall down onto here. Some of the wind will blow and let it gather up here. Snow tends to gather around a mechanical unit and a parapet. So we have to build in an accumulated snow load factor, and it varies where you are on the roof. It is a rather rigorous calculation, which is why it's beyond the scope of this course, but you need to understand it exists. It's really important if we're building a low building beside a tall building. This building is going to cause weight, snow, extra snow to pile up right here. If we're building a building with a mechanical unit, or even worse, putting a new mechanical unit on an old building to give it upgrades, we have to worry about the accumulated snow load around it. Parapets, we're going to get accumulated snow loads. The really interesting one is if we're the ones designing a new tall building beside an existing low building. Our building is causing snow load to accumulate on the building beside it that didn't exist before. The onus is on us to do whatever we can to investigate and fix that situation for them. So we have to try to communicate with them, let them know what we're doing, and try to fix their roof for them in a way that it can support the snow loads. So we can send memos, we can send letters, we can say we have permission to build this building next door, here's what we're going to do, we'd like to come in to investigate, and then if extra requirement is needed, it's our responsibility to pay for it. They cannot protest the building by saying no. That isn't part of what it is. If you have your permit and you're allowed to do it, the onus is on you to do whatever is reasonable to investigate that situation. But if you have a neighbor of your client who is just saying, no, I don't want that building built and here's how I'm going to protest, if you can prove to the city you've done everything you could, they now have the responsibility on themselves to investigate and make that repair themselves. And the city might order them to, because now it's a life risk issue. So you just have to be able to document that you've done everything you could, and if they're compliant and willing to help out, to actually add that in. So let's do a quick example. We'll try to do it quick like this. If not, I'll do an extra slide where I actually write it out by hand. But you're going to see that everything is written out here for you. So what is the snow load on a flat roof of a building in Toronto for a condo if there are no buildings taller than it nearby? So that taller than it is giving us the hint that we don't have to worry about accumulated snow load, which I've told you I'm not going to give you questions that you have to worry about that for. So they've said no accumulated snow load. It's a condo, so it seems unlikely that anything weird would be going on there and that it's probably a flat roof. We know that it's in Toronto, so we can look up SS and SR. It's also in Toronto, so it seems unlikely that there'd be nothing around it. So it seems like our exposure factor, or our wind factor, should be 1. Let's take a look at all of our factors. Our slope factor. It's a condo. I can't think of any condos that have sloped roofs. They're usually pretty standardly flat. So we know our equation is importance factor times, in brackets, our snow load times our CB times our CW times our CS times our CA, then plus our SR. After that is when we can multiply it by our importance factor. So, importance factor. For our snow load, it doesn't seem to be an unusual type of building, so it seems like it's reasonable to say it's a normal importance building, which I've told you, unless I tell you otherwise, these bad boys are going to be regular. I would tell you pretty explicitly if it wasn't regular. So regular just means our importance factor is 1. SS we have to look up. CB, I've told you that for you guys, CB is 8. It's our ground load, it's our roof factor. So we have snow hitting the ground, some of it falls off, we only have to use 0.8 of it on our roof. CW is that wind blowing snow away from our roof or off of our roof factor. I've told you it's probably always going to be 1 for you. And Toronto, it kind of makes sense that there's not going to be nothing around this building for an entire kilometer, so 1 makes sense. CS is our slope factor. There's nothing telling us it's a sloped roof, so it's probably in our best interest to assume that it's a flat roof, and we're going to use 1. And then CA is the accumulation factor, and they've said there's no buildings taller than it, which means there's no likelihood of accumulations piling up. And I've also told you it's beyond the scope to do more than that. So it looks like the only thing we need to do now is look up SS and SR. It said it was Toronto. Let's come back here. Toronto, they've said Toronto explicitly. I think they would have said Etobicoke, North York, or Scarborough if it was otherwise. But we've got Toronto City Hall. SS is 0.9 and SR is 0.4. So now we have our SS and SR for our 1 in 50 year snow load event. So importance factor is 1. SS was 0.9. SR was 0.4. CB is 0.8. CW is 0.1. CS is 1. And CA is 1. This looks like a pretty simple calculation. We can plug this all into our calculator, being smart about our brackets, and we get our snow load for this condo in Toronto is 1.12 kPa. So now we have a snow load that we can use to design our roof members with. Rain, we have a wet factor or an associated rain load in our design there, but we also have a rain load. It rarely governs in most of Canada, Toronto included in that, but I want to talk about it because sometimes it can we need to design for it. And the city is very, very diligent in checking on that. It's something that they really ask a lot of questions about, and you need to be able to document what's going on there. So my kids are now watching through school Cosmic Yoga. If you haven't done it, it's wonderful. It's a kids-based yoga, but it's very soothing. So they're just having a little yoga workout right now. So all roofs in Canada need to be designed to support a 24-hour rainfall, assuming there's no slopes. It only tends to govern if there's a large slopes to an internal drain on the building. We have to assume that any drains or scuppers in a parapet, if there's no parapet whatsoever and it's a sloped roof, this isn't going to be a thing you need to worry about. But that condo we were just talking about probably has, a tiny little curb around the roof just to hold in all of our roofing, and water can kind of accumulate there. We probably have a little scupper where the water falls out. Maybe internally in the building there's a drain that runs down through the building. We need to assume that all of those things can get clogged, and that rain could accumulate on our roof for 24 hours for our 1 in 50 year rainfall event. So that means we could accumulate 24 hours worth of rainfall in a big rainstorm. It can happen. I have seen buildings get their leaves clogged up. Now, this assumption is that after 24 hours, you're gonna go up to your roof if you've had the biggest rainfall you've had in 50 years and clean those out. If anyone was living in Toronto in 2012 or 2013, when we had that massive, massive rainfall, let's go back and take a look at that Toronto data. And look here. So Toronto, it basically hit Toronto and Etobicoke the hardest. Let's come over and we can see here that we have a 1-day rainfall, which is 24 hours. And that's our 1 in 50 event. The rainfall event for Etobicoke, we have to be able to store 108 millimeters of rain for 24 hours. And 97 millimeters of rain in the downtown core Toronto. That storm in 2012 dumped 127 millimeters in 2 hours. So that far and beyond exceeded the 1 in 50 year 24-hour rainfall event. We've since had other ones that are pretty darn close. It wouldn't surprise me in the next iteration of the code if some of these numbers change due to climatic changes that we're seeing across the world. But luckily there was very little, there was damage to buildings, but no loss of life due to collapse of buildings, which means there's something we've done here that makes our roofs stronger than that alone. And that's what we're going to start to talk about in a few minutes with load combinations and reduction factors. We build in some extra safety there because we might end up worse. These are just about statistics, remember. We want to reduce the risk of loss of life. Making everything zero, it would be too expensive. I always say too expensive to design for the apocalypse, but we can get as reasonably close as we possibly can. So let's go back to that. So when would rain load govern? Now, I said this is about storing 24 hours of rain on a roof, assuming our gutters and our scuppers are clogged. So if this is a roof, and that's our 24-hour volume of rain, acknowledging that there's depth to this, we'll often put a drain in the middle of the roof and slope our roof down to that drain. So this is exaggerated, obviously, but this is what we might do to our roof. That volume of rain doesn't change. That 24 hours of rain still stays the same, but look how it might get distributed on that sloped roof. Here in the middle, that's our depth of water. Well, look here in the middle now. We have a much higher depth of water. Over here, we actually have less. But we have to think about this because in a roof that's sloped to drain with large slopes, in our 1 in 24 or 1 in 50 year 24-hour rainfall event, we might have local spots that see more rain than our snow load design might be. So we might have a few members. If we had a beam kind of running kind of into the page right there, we might have a beam that is seeing more load than the rest of the roof, and we'd need to design for that. I have to sneeze. Oh. So let's move on to wind load. Wind load calculations are pretty intense. There's a lot of things we need to consider. I'm going to say that for you guys, the calculations are beyond the scope of this class. I want you to understand what we're talking about with wind, what aspects we're designing for wind, because there's different bits, the way we think about it. And also, I want you to understand that it's a lateral load, but it's not just a lateral load. So when we're talking about wind, we're often talking about what's causing this building to try to tip over like this. You can imagine if the wind is blowing in this direction, we've got our windward side wind and our leeward side wind. So one side is trying to push and one side is trying to pull, but they're both going in the same direction. So the values are different because it's going to be worse on the side that it's blowing on and a little bit reduced on the side that it's trying to pull. But we add those up for the building as a whole. We also, as the wind passes over the roof, it swirls and does stuff. Sometimes it can try to push the roof down, and sometimes it can try to lift the roof up. And that's what we call roof uplift. That's another thing that the city will often require a report on. So when we submit for our permit, we often have to show a roof wind uplift diagram so that the city can see that we did that check. We also have to design for components within the building. I'll talk about that in a second. We also have to design for the elements itself. So there's the building as the whole, but then what about the cladding? That itself needs to be able to work for the wind load that's being applied to it, and it's got an exterior wind load on it, but also some component of wind on the inside. And you're probably thinking, how's the wind on the inside of the building? But it doesn't matter how well sealed your building is. Some wind gets in through the leaks and cracks, and you can get some suction. So we have an interior and exterior component to our exterior wind load. We can also have interior wind loads due to mechanical systems. We'll often want air blowing in a certain direction where we heat one zone and cool another to force air to flow in one direction. And that causes an internal wind pressure on our walls as well. The wind equation looks kind of similar to our snow equation, where we have Q, which is our reference wind pressure. This is from climatic data from the code, similar to the way we looked up our snow load. And we have an importance factor, a thing that we know that we can look up from that importance factor chart. And then we have wind factors. CE is the exposure factor, dependent on the height and terrain. If anybody's ever read Ken Follett, Pillars of the Earth, they keep having the big building they're trying to build collapse. And they can't quite figure out why. And it's as they're building it taller and taller, they realize that as you get further from the ground, the wind loads increase. That is essentially what our exposure factor is, that we're accounting for wind increasing as you go higher. CP is a pressure coefficient, and it's dependent on the shape of your building. CG is the gust factor. So if you've ever stood outside and you see a tree moving off in the distance and you're just feeling a light breeze, and then a few seconds later you feel a big gust, but the tree isn't, that's because as much as there's a steady wind, there's gusts as well. And the way we apply the gust factor is depending on how big the element we're talking about is, the gust factor changes. If we're talking about the building as a whole, well, it's probably the distance from me to the tree. That gust isn't impacting the entire building all at once. So we apply some component of it to the building as a whole. But if we're designing one window, which is very small, when that gust hits, it could apply to the entire window all at once. So we'll use a higher gust factor. So again, here's that same chart. We have Toronto, Etobicoke, North York, Scarborough, Toronto City Hall, where over here we had our snow load and our rain load. Well, over here we have our hourly wind pressure. Again, they list it in 1 in 10 year and 1 in 50. We're doing 1 in 50 year design. That's our return period for a big damaging storm. And you can see here Toronto City Hall, 0.44 kPa for a 1 in 50 year wind event in Toronto. Like I said, we can have interior wind loads due to mechanical systems as well. So I already talked about this. Seismic loads are another thing that are a bit beyond the scope of this course. I want to touch on it for just a minute because it's helpful to understand, A, that it's a lateral load, similar to our wind loads. It's trying to knock the building over. But it's essentially, as the ground moves, it tries to take our building along with it. And instead of saying, how much is the ground trying to move, what we say is, what's the acceleration of the ground? Or how much is that ground going to try to drag the building instead? So instead of looking at it in that way, we say, okay, what is the amount the ground can move, but apply it as a load at each story of our building. Our building has a weight, and what we say is, depending on how much the ground is trying to move, the force that's trying to push it is dependent on its weight. And that varies as our building goes up, and the dependence on how tall it is as well. So, heavy floors move more. Light floors try to move less. High floors try to move more. Low floors try to move less. So a high, heavy floor is trying to move the most, which means that we apply the most load to those floors. I've said that structural design hasn't really advanced much or had much development in 100 to 150 years. One of the places that is not true is in seismic loads. Seismic loads have seen real advancements in the past 50 years, mostly due to our analysis software. We have been able to make our design much more complex to make our buildings more resilient and less expensive. Resilience, or you can use resilience in a few different ways. Maybe make our buildings more ductile. Ductility is all about movement and how much we let our building move. Movement also absorbs energy or takes a certain amount of energy. What we say is, as our building moves, we will allow that movement to actually reduce the load our building sees. In Toronto, often we don't do that because seismic doesn't tend to govern, or if it does, it's a reasonable design, and the cost of the extra material to build it is not offset by the engineering costs. So we could go through this complex, rigorous design, but the engineering would be really expensive and we'd see almost no savings in our building. In places like Vancouver, Ottawa, and northern Quebec, that is not only cost effective, it's a code requirement, where we go through and we do a very rigorous, complex design to try to A, reduce material, and make our building safer. You would think that taking build material out wouldn't make it safer, but we take it out in a very strategic way, in a way that allows our building to move in a very explicit manner, hence absorbing more energy, hence making the building more likely to survive a large-scale seismic event. The way we used to do it And it's still loosely based on this, as we used to say that the building would move as a percentage of the weight of the building. So for you guys, that's an easy way to think about it. Toronto back in the day, probably 15 to 20% of the weight of the building would be what we would use as a lateral load, distributed as we went up the building, where the upper parts of the building saw the majority of that load. Again, beyond the scope of this course to do the math, but I need you to know it exists and what we're talking about there. And especially if you move to someplace with a high seismic zone, you want to at least understand where these concepts are coming from, because it becomes a big part of the design. I always tell architects and engineers, it's never our job to tell an architect no. It's always our job to try to find a reasonable solution and to make you aware of the cost and implications of that solution and possibly provide a cheaper alternative. But it's not our job to say, no, you're not allowed to do that. One of the few places in the code where it explicitly says you cannot do these things is in the seismic portion of the code. It varies on region and what your building type is, but there are a specific set of clauses that say if your building is this, you cannot do this. Most of those don't apply in Toronto, but we need to be aware of them. One of the things we can't do is have a weak story. What that means is if we have a rigid, stiff building up here, then this floor down here has enough lateral load resisting system, or the thing that stops our building from tipping over, to resist all the loads, but it is much weaker than the floors up here. It doesn't matter that this is strong enough, we're not allowed to do it. And some of that is because they've seen that the biggest causes of loss of life and damages have been when buildings have shifted at one whole story because we had a weak story. Even though it was strong enough, that shift above was so much that it caused a kind of implicit collapse. So we are not allowed to do that, and depending on where you are in Canada, there's other clauses we're not allowed to do. Some other load types that I'm just going to touch on quickly. Soil pressure. You can imagine that soil sitting, if we dig out a big hole in the ground, and I think I talked about this a little bit, you dig a big hole in the ground, you get a nice perfect hole, and then a bratty sibling comes and stands beside the hole, and all the sand falls into the hole. That is what soil wants to do. The weight of it is trying to shear it or push it into that hole. So we put a foundation wall in to stop it, and we need to know what load that soil is pushing against that foundation wall with. And that is dependent on the weight of the soil and the things on the soil. So we get a soils report from an engineer, and they tell us A, which is the earth pressure coefficient. I often call it the sticky factor, or how much that soil is going to bond together. Q is the surcharge, or remember those fire trucks we had to worry about? That would be the live load sitting out here on our soil. K again, and then we have the weight of our soil. So at the top, there's almost no weight. We're going to have almost no load trying to push in. But as we get down to the bottom of the foundation wall, we have all the weight of the soil above it and the weight of the surcharge trying to push all of this soil into our basement. And we can see that the pressure starts to increase there. I'll come back and do this calculation, maybe we'll go through and do it verbally. It's still not a complex calculation. We have the equation right here. And you can see that this pressure of the soil trying to push in varies as it goes down. It's lighter at the top and more at the bottom. So a house has a 10-foot basement. The soils report tells us that the earth has a pressure coefficient, or that sticky factor, of 0.3, and the soil has a weight of 20 kilonewtons per meter cubed. Assuming that there's a laneway adjacent to the house, so that means big trucks could roll down there right beside the house, so we should probably think that the surcharge would be 12 kPa of live load. What is the soil pressure at the top and bottom of the wall? So we know our equation is pressure equals K times Q plus K times gamma times H, or the height. So we're probably going to need to check this top and bottom, and we saw that it varies linearly as we go down for height. So we know K was 0.3 from the soils report. They gave us that. Q, we know, should be 12 kPa for a live load if there are vehicles beside, outside of a building. So those big fire trucks were going to be 12 kPa. We could look that up, and I talked about it at the beginning of the lecture. The weight of our soil is 20 kilonewtons per meter cube. So every 1 meter by 1 meter by 1 meter cube of soil weighs 20 kilonewtons. So that's a lot. That's 20 Arnolds jammed into a 1 meter by 1 meter by 1 meter box. At the top, our height is 0. And at the bottom, our height, we need to convert that 10 feet into meters because we're talking about things in kPa and kilonewtons and meters cubed. So we want all of our units to be the same. So 10 feet is, and there's 12 inches per foot, so 10 times 12. And then there's 25.4 millimeters in every inch. But we want to talk about this in meters, and there's 1,000 millimeters in every meter. We get that 10 feet is the same thing as 3.048 meters. So we can do that calculation. We're just going to plug all of those things into this soil pressure equation twice. At the top, we've got 0.3 times 12 plus our 0.3 times 20 times 0, because at the top there's no height. So it looks like the only thing causing this to try to push in is the surcharge, or 3.6 kPa trying to push in sideways. At 10 feet down, which is about a normal basement, we have 0.3 times 12, which is that same surcharge load, plus 0.3 times 20 times the height of where we are, which is 3.048, giving us 21.9 kPa at the bottom of the wall. Again, that is a large, large load. You can see that as much as we don't talk about it much, it's a massive load. Luckily, concrete is kind of robust, and we have concrete everywhere. It's why concrete is great for a foundation. It's along every surface of that wall. So every tiny little bit of that wall is working for us. So foundations, people ask, why do we always do concrete foundations? This is one of them. We have to hold that soil back everywhere anyway, and doing it in steel, the advantage of steel is we can do big pieces of work discreetly. So concrete is a no-brainer for foundations, for most foundations. Temperature. If we have one side of our building heating up in the sun, and the other side is cold, we can see contraction on one side and expansion on another. We can see big scale movements. If our building's enclosed, doesn't really tend to matter. We're usually governed with an internal climate. So we might see, 15 degrees to 30 degrees inside a building. It tends to be governed pretty tightly. Buildings that aren't, we need to worry about these kind of expansions and contractions. Not as big of an impact on concrete and wood buildings, although we do have to think about it. Steel buildings tend to be a big one that we have to think about it. If we have a large building like an arena, we still have to think about it, even though it might have a climate control on it and all the elements inside an envelope. It's big enough that you can see differences over the building that we might need to take into consideration. Pre-stress. Pre-stress is when we tighten something and hold that in place in some way so that when we apply a load, we're not trying to squash it, we're actually unloading the pre-stress. Anyone who's used a saw knows that unless you have that handle clamped, that blade will just buckle, and what you're doing there is pre-stressing it. Most of these ones are beyond the scope of the class. I just want to point out that they're all things that we do think about. Sometimes we think about them and say, okay, that's not a problem, but we have thought about it. Vibration. We have a few different types of vibration. We talked about these last week. There's the continuous vibration for people moving. There's damped, which is a single impact load that dampens off. And then we have amplified, where we have things that can get amplified because it resonates at the same frequency of the building. we're not going to go too much into that. So now I want to talk about load combinations. This lecture is going a little bit longer than I had hoped, where I've broken it up into a few sections. I've kind of lost track of how long we've been going. So strength, we've already seen this slide where we used to say we had a load on the system and we took all the loads, added them up, and then we applied a factor of safety. And that had to be less than the capacity. So the only place we built in any redundancy was the same factor for all the loads, and that was it. What we do now is say there's different loads on the system, so we'll apply factors based on what load type it is, and we'll also reduce the capacity so that we're giving everything its due attention. Oddly enough, this does not mean we over-design things or we've made things bigger. It's actually had the opposite. We've actually thought about loads specifically and their possibility of occurrence, and we've thought about materiality and its possibility of failure. We've actually been able to refine buildings because of this. So we factor the load, and it has to be less than the reduced capacity. And that little sub F means we've applied our loads, and that little sub R means we've reduced the capacity. And like I've said before, I'm going to show this slide again and again and again and again. This is limit states design. And we do the same thing when we talk about serviceability. It's just that our factors are usually 1 and our reduction capacity is 1. But ultimate limit states, and then we do the same thing when we talk about serviceability limit states, mostly just to help us organize our conversation. So ultimate limit states, or our ULS design, is all about strength. Serviceability limit states, or SLS, is all about serviceability, or when we're talking about those finishes cracking. We're going to talk about load combinations now. So this is how we increase those loads, or those factors we apply to the loads. Remember I said the table, we would have the thickness of it. If Shannon was standing on a table and we're designing that table for Shannon, maybe they made the table slightly the wrong thickness. Well, that's a dead load. The weight of the table is a self-weight dead load, and maybe it was a millimeter thicker than it meant to be. And Shannon might have gone out and had a cheeseburger and beer. I might have worn a Barney costume that was heavier than my normal clothes. So Shannon has much more variability than the table itself. So we would increase the load on Shannon more than we might increase the load on the table. Mostly because we've designed, we've said exactly how thick that table wants to be. And it's pretty easy to make it what we want it to be. But we do build some safety in just in case. So what we say there is we have to look at a series of combinations and think about which one could be the worst. We have our principal loads and companion loads. They're all the same types of loads, it's just how we're combining them. We change around what we're talking about. We have to think about all of these. So in our load combinations, let's look at the first one, is 1.4 times dead with nothing as a companion load. So 1 principal load, 0 companion loads, and we take all the dead loads, so that's self-weight and superimposed, and multiply it by 1.4. Often it doesn't govern. It might govern if dead load is really, 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 really high. We still have to check it, but it often doesn't tend to govern. It might govern for contractors doing their component of the work or their scope when it's just dead load on the site. The big ones that really tend to govern are the next few. So here we have 1.25 dead. I'll come back to this 0.9 dead in just a second. So 1.25 dead plus 1.5 live. So we have to say, okay, let's think about 1.25 dead plus 1.5 live. And then we have to do it again, including our companion loads, which could be 1.0 snow loads or 0.4 wind loads. We don't do snow and wind both as a companion load at once. This one line here, let's ignore the 0.9 dead for now, has three separate load cases that we've talked about. Dead and live all by itself, dead and live and snow, and dead and live and wind with their appropriate load factors. So then we have to do the same thing where snow becomes the principal load and live and wind are the companion loads. So three more load cases that we have to worry about here. Then we do the same thing again where wind is the principal load and live or snow load are the companion loads. So three more load cases that we have to think about. Now let's come back and talk about this dead load. We use 0.9 dead load if it is helping our total. People always say, what do you mean by helping your total? We're going to do a calculation in a few minutes, but briefly, if all of our loads are talking about squashing something down, our dead load is squashing it, our live load is squashing it, and our snow load is squashing it, but we have wind trying to pull up on that thing. Well, dead pushing down with a factor of 1.25 and wind pulling up with 1.4 isn't the worst case because they're acting in opposite directions. Snow and dead and live pushing down will be the worst case for downward stuff, but windward pulling up, live would make it go down, snow would make it go down, so we need to think about wind without a companion load, and we want to say that because the dead load is pushing down, we don't want it to push down too much. What if we overestimated the weight of our dead load? We want to consider the fact that we might have overestimated, so the other direction, and say, okay, now we have to apply a factor of 0.9. So in that case, it would be 0.9 dead load acting downward and 1.5 wind load acting 1.4 wind load acting upward. And then we do that with live and wind, or we might need to think about companion loads, but if they're acting in the same direction. So you really have to stop and think about it. You have to think about what direction they're acting, and are they adding up or subtracting from each other? Because if they're subtracting from each other, you want to get the worst case of the load acting downward and the worst case of the load pulling up. And then seismic, we have to think about just dead and seismic load. And remember, seismic is a ratio of our dead load. And we have to think about dead load, earthquake load, plus live load and snow load. We do add them up here. So we have two cases here. We have dead and seismic, and then we have dead and seismic, live, and snow. The idea there being is that earthquake might be pushing down or pulling up. And so we want to look at the case where we have just dead and seismic, where dead's acting down and seismic's pushing up. So we have two worst cases that we have to think about there. So these start to really add up. Keeping track of things becomes the really hard thing to do. So how do we keep track of these? Having a good nomenclature system is really handy. I like to use this system where I remind myself that the U means I'm talking about an ultimate limit states combination, and then I put the names of my loads here to help keep track of it. So that first case, which was 1.4 times dead, I usually put UD. You can come up with your own naming system. It doesn't matter to me. I have found that anyone I show this to has adopted it. My husband's office of 60 people have all adopted this nomenclature system. I've actually even gone other places where other people on their own have come up with this exact same kind of naming convention, because it's a pretty obvious system and a pretty easy way to keep track of things. So you can see here that then we have the case with just dead and live, dead and snow, and then the condition with dead and wind. Then those ones where live is the principal, snow is the companion. Live is the principal, wind is the companion. We go through and we do that again and again and again. Then look here, we have the one where we have 0.9 dead plus 1.4 wind. I'm assuming here that dead and live and snow are all gravity loads and wind is upward. We don't know that for sure. We'd have to think about those things multiple times, but often that tends to be the case here, but not always. But I'm showing it here because tends to be the norm. And earthquake can often go in either direction as well. So we have dead and quake, and then we have dead, quake, live, and snow. So that's a lot of load combinations we need to look at and see which one governs each of the things that we need to talk about. But we have a building. Wind can go this way, wind can go this way, wind can go this way, wind can go this way. And same thing with seismic loads. So it seems like we need a few more load combinations. Now we've got wind in my X direction, acting in that direction, wind in my X direction, acting that way. I'm going to call it positive and negative. Y direction positive, Y direction negative. So for all of the wind and seismic cases, we actually have 4. So any ones that had a wind or a seismic in it, we had to multiply by 4. So now we've got a ton of combinations. But it gets actually even worse. We try to build in the ability that our building might rotate a little bit or try to twist because of these loads. And sometimes we'll lump wind at the corner of a building. So we'll lump it over here, and then we'll lump it over here. And then we have to do the same thing in that direction, and that direction. So anywhere we had 4 wind combinations before, now we have to have 8. And same with the seismic. So now we've increased this even more. So that's a ton of combinations. I'm not even going to show you more of them. I've done projects, you can imagine, again, on top of that, we might have a wind analysis done of our building or a snow analysis done of our building. That Canadian Peace Bridge Plaza that I showed you at the border crossing, we had snow and wind analysis done of those. I ended up with over 1,200 load combinations that needed to be considered. And every time we made a change in the design, strength and stiffness needed to be recalculated for every element, every connection, and every system on the building. So that starts to be a really kind of rigorous process as we go through the design. Serviceability, a little bit easier. It's all one, except back here, we had our ultimate limit states importance factors involved in it. Here, it's the same loads, but we've got to remember that when we're talking about snow or wind, we have to add in that serviceability importance factor. So remember for snow, that was 0.9. So we'd want to take whatever that snow load is and add in our 0.9. So for a roof, we have to look at dead and snow added up, and snow all by itself. And this is where those 2 criteria come in, because we had a criteria for dead and snow together and a criteria for snow by itself. But you can see the loads are different. So how much they move will be different, which is why we compare them to 2 different values. So we do have to keep tracking those. There is no, this is the maximum amount the beam can move. It really has to be, this is the amount it can move under dead and snow, and this is the amount it can be moved under snow. And then we have to check those against how much they actually do move. So let's do an example. It looks like I've already written out all the answers here, so I didn't make it come in on an animation, but we can talk through it. So here, we've got 12 kilonewtons of dead load, and they're saying it's in compression, so downward. It's trying to squash this thing. We've got 10 kilonewtons of live load in compression. We've got 5 kilonewtons of snow load in compression, and we've got 10 kilonewtons of wind in compression, but also sometimes in tension. So it's part of a system that's making the wind blow back and forth, and in one case it's pulling upwards, in the other case it's pulling downwards. So we have to think about a few combinations. We know the very first one is dead by itself, which is 1.4 times dead, or 1.4 times our 12 kilonewtons. Our dead and live case, so these are all still ones acting downwards, so we don't have to worry about that 0.9 dead load just yet. If they're all acting in the same direction, we want the worst of all of them. So that's the 1.25 plus whatever factors we're talking about for the other loads. So dead and live, is our 1.25 times our 12 kilonewtons plus 1.5 times our 10 kilonewtons, or 30 kilonewtons. Snow is 1.25 times 12 plus 1.5 times 5. So those were those all by itself. Now we need to start thinking about those cases with companion. Oh, look, we have one more. 1.25 times 12 plus 1.4 times 10. In the wind case acting downwards, these are all the downward ones. I'll worry about wind acting upwards separately at the end. Now we have to do all of those companion loads. So 2 principal loads, dead and one of the major loads, plus the companion load. So let's start with live as our principal. So we have dead, live as our principal, and snow as our companion here. We have dead, live as our principal, and wind as our companion. So see, look, with its snow, it's 1 as our companion, but only 0.4 for wind. We have dead, snow as the principal, and live as the companion here. Dead, snow as the principal, wind as the companion. And then we do it again where wind is the principal and live or snow as the companion. And we add all those up. Now, let's stop and think about the condition where wind is pulling up. Anything acting downward is going to make that upward force less. So let's not worry about the ones, I guess the worst case could be wind all by itself pulling up. But we know that there is dead load there. But we want to be careful we haven't overestimated how much dead load is trying to hold that down. We could have this condition where there's no wind, no live load, and no snow load on this building, and the wind is trying to pull it up. And in that case, we only use 90% of the dead load pushing down, or 0.9 of our dead load. And that lets us look at the worst case upward force. So 0.9 times our dead load minus, because remember the dead load's acting down and the wind load's acting up, they're acting in opposite directions, 1.4 times our 10 kilonewtons. And that gives us 3.2 kilonewtons acting upwards. So downwards, it looks like dead load with live load as the principal and snow load as the companion was our worst case compression load, and we have a tension case where we have wind with some dead trying to hold it down. So we have a worst case compression, so CF, because these are our factored loads, we've applied our load factors. CF, which is C is for compression, is 35 kilonewtons, and our worst case tension is 3.2 kilonewtons, trying to pull up on it. So now I just want to touch on a few loose things because things are going to start to move faster going forward. And I want to talk about tributary area and tributary width. This is something that surprisingly you intuitively understand. The second we try to draw it and talk about it is when you get it all muddled in your head. So stop, take a look, really look at the drawing, think about what the thing is doing and where the load is going, and that will help you understand what these tributary areas and tributary widths are. You do have some exercises with those things in your assignments and quizzes. And then I'm going to just briefly show you some drawings that you can go through at your kind of relaxing pace. I used to not even do that in this course, but I just wanted to give them to you to help you out a bit. So tributary area is the area that there is a load acting on that impacts the thing you're designing. Not everything in the building has the same tributary area. For the same object, different loads acting on it might have different tributary areas. And I find the best way to talk about this is with something you intuitively or inherently understand. So let's talk about a watershed or a tributary. They have the same name. So a tributary is a watershed, and it's the catch basin of water that falls in a region that impacts a thing. And hydrologists and hydraulic engineers use this to figure out like flow velocities of rivers. So if you were walking through the woods and you came across a running body of water, you'd probably call it a river. It's only in the context of looking at a map would you know whether that was big, medium, small, or little. You might have been looking at a brook or a creek, and those are just colloquial names to give us a hierarchy within our system. They don't mean anything. They're all technically rivers. They're all flowing bodies of water, but we colloquially give them names to help us understand where they fit in the hierarchy of the system. We're going to do the same thing in our buildings with beams, because we're going to give beams different types of names, especially as we go forward in the course, and that's going to be really handy. So you come across this river in the woods, but maybe you come across a different river in the woods, and then you go back and you look at it and see it was a mid-sized river, so maybe you'd call that a creek. Again, it doesn't matter what the actual names are because they're all rivers. We're still just talking about rivers no matter what here. So now you're going through the river and the woods and you come across a different river. Now you go back and look at a map and see, oh, it's a much smaller one. That one's actually a stream. And maybe again, you go and you come across something, but this one's really tiny and it's a brook. But look, a creek could flow directly into a river. A stream could flow directly into a creek or a river itself. A brook could run into a stream, a creek, or a river. So being a brook doesn't necessarily mean it has to go into a stream. It can go directly into a river. We're mostly talking about kind of how large it is and what job it's doing. And it's going to be a little more explicit in our buildings, but I do know it's a thing people still struggle with. So in a large river system, we know that it could be snowing in one region and raining in another. Well, snow and rain are loads that we use. It could be sunny in part of the system. So just because there's snow on that watershed or that tributary doesn't mean it's on the entire tributary. For the brook, if it is snowing in this region, it's probably snowing over the entire brook region. But when we talk about it in terms of the river, that snow is not impacting the entire tributary of the river. It might be impacting the entire tributary of the brook, but not the entire tributary of the river. A hurricane might impact the entire tributary of a river system. Still kind of unlikely because you get different intensities. So, very similar to how we think about buildings. So that might be the tributary of a brook, something quite small. A stream probably has a larger tributary area picking up brooks. Our creek might have an even bigger tributary area picking up creeks or other streams. And we could have a river that has a very large tributary watershed or tributary area, picking up different types of loads in different areas. So that would be the overall tributary region of it, but it doesn't mean that entire tributary region is applicable for every single load that the system is seeing. So let's look at that as if it was a building. We can have columns, and we can have girders, and we can have beams, and we can have purlins. Here's the interesting thing. Girders, beams, and purlins are all beams. Yes, they are all beams. They all do the same job. They just do it in a slightly different hierarchy. So if I am talking about a beam, you do not know if it's a purlin, a beam, or a girder until you look at what job it's doing, or if I tell you explicitly what job it's doing. And this is going to be important when we look at preliminary sizing of elements. So our 5th floor purlins might see one live load, and our 4th floor purlins might see a different live load, even though they're all eventually coming down to the same column. So the same tributary area does not impact every single area or the entire area of one element simultaneously. So the building, let's look at this. We have our columns, kind of doing the job of a river. Girders are kind of the next level of the hierarchy. They're usually doing some heavy hitting. They're usually doing a big job. They are usually picking up a beam or a transfer of some sort. Beams are rather kind of mid-range, doing a job but not too much job. The lightest jobs on the project are usually the purlins. There's usually a bunch of them and they're picking up the deck or whatever the big flat thing is that we put everything on. So the purlins tend to pick up those. The beams tend to pick up the purlins, or the beam type that picks up purlins, we tend to call beams. And the beam type that tends to pick up other beams or other columns is what we tend to call a girder. And so you can have different loading in different regions. Tributary width is when we don't look at the entire area, but we keep it in just what portion of that is being loaded. And this is really handy when we're talking about beams and purlins. So if we have a plan here where we have 3 bays of 6 meters and 2 bays of 8 meters, and we have a bunch of different columns and a bunch of different beams and purlins. These dashed ones could be joists or purlins. There's a deck spanning in this direction, sitting on all of these elements. So all of these elements right here are directly doing the job of picking up the deck. It doesn't mean that these ones don't pick up the deck, but most of the load on these ones is actually coming from the fact that we've got these purlins sitting on it, or open web steel joists. These we would call a beam. And then here we have some columns. So let's look at RJ01, or roof joist 01. Its tributary area is this whole area. It's picking up some portion of deck from here and some portion of deck from this side. So half of the amount of deck that's spanning between here. This is going to do the work of carrying it. And half of the deck between this zone is going to go to this joist. So this is our entire tributary area, or 8 meters times, well, we have 2, 4, 6. 2, 4, 6, so 1 meter and 1 meter. So 2 times 8. So we have the entire tributary area there. But let's look at the tributary width as well. Oh, actually, so the tributary width here would be 1 meter and 1 meter, or 2 meters. So we have 2 meters times its length, which is 8 meters. So tributary width would be 2 meters. Tributary area would be that 2 meters times the 8 meters, or 16 meters squared. All of these joists have the exact same tributary width and tributary area, so we'd probably call them all the exact same thing. Let's look at RB01. RB01 is picking up half of all of these joists. So it is picking up it's doing the work of picking up half of all of that. Its length is 6 meters, and its tributary width is 4 meters. It looks like all of these beams are doing the exact same job. Thought I had these all color-coded. RB02, all 3 of these are doing the exact same job. They're picking up half of the joists on this side and half of the joists on this side, and they are 6 meters long. Column 1, it is picking up this quarter of this piece of deck, or half of what's coming from this beam and half of what's coming from this beam, acknowledging that this beam is picking up half of these joists. So its tributary area is going to be half of the 6 meters times half of the 8 meters. And we've got 4 columns doing the exact same amount of work. Column 2, we can see that it's picking up half of this beam and half of this beam. And we've got a few more doing the same thing. Dave, can you do me a favor? Can you get the kids lunch? They have 2 bits they have the leftovers from the past 2 nights and plates there. And just, maybe Jackie already did it, I'm not sure. Sorry, I didn't want to stop you guys again. C3 it's picking up half of this beam and half of these 2 beams. So we could draw its tributary area like that. Look, it's got another column doing the exact same thing over here. Column 4 in the middle is picking up half of all 4 of these things. So we can draw its tributary area as looking like that. I know I have made these colorized somewhere, so I'll go find those and I'll re-upload your slideshow, just because it helps out. It makes it a little bit easier to see. So I'll go find that. It's fine for this presentation, but I'll upload that seconds after I upload this for you guys. So if you're not seeing that, it means you downloaded it prior to me uploading this video. So just take a second and pause it, go back and get that other, yeah.
Which one?
Both, well, divide the lunch up for them in a way that makes them full. So here we have some little drawings kind of showing what that math was. So look, here's that RJ01. I've written out that its tributary width is 2 meters. Don't worry about these calculations. That's beyond the scope of this class. I just wanted to show you that we have a tributary width of 2 meters. We will get into this, but that's a little bit beyond what I wanted to talk about today. And here's the entire tributary area, which is that tributary width times its entire length. And so I talked through all of these, so you have all of them right here to take a look at. What happens when things are crooked or weird? Well, this beam right here, beam O2, picks up half of each one of these joists, and these joists get shorter. So we could draw a line through all of those halfway points. And it picks up half of all of these joists. So we can see that its entire tributary area is this, and its tributary width, oddly enough, stays the same over its whole length. That's not gonna be... Oh, you're gonna have to go eat your lunch, buddy. While Jackie moves the table, she'll come back and get you. So we can see that even though these vary, the sum of both sides kind of evens out. I know. So these two do the same thing. Picks up half of all of these, and it picks up half of all of these, and these tributary widths stay the same. So oddly enough, these 3 beams are all going to end up with the same design. These 2 beams, new slide. This beam here picks up half of each of one of these open web steel joists, and that length varies. So we have an uneven load distribution along this beam. So it's going to change over its length. So it's not going to be a uniform load on it as it goes down. Okay, Dunky, Jackie's ready to give you lunch. Rah! Go eat some lunch. And these 2 beams, same length, same load distribution. Assuming they had the same load on them, we could design them as the same beam. These should probably have different names, but these 2 beams are going to be the same, and these 2 beams are going to be the same. We might say, all right, that's a lot of work. All 3 of these beams are kind of similar. We're going to design it for the worst case. So acknowledging that all 3 of these have different load cases, we might only design one of them and apply it to all of them. We have to be very diligent in how we track those things. I would expect you guys to keep track of them as 3 different beams. Okay, now I'm going to just quickly show you some slides that is beyond what I would normally do in this course, but I've uploaded all of these things to your download module in Quarkus, and they're just things that are going to help you get comfortable looking at drawings. Take a look at them, review them. I've made a fake building for you to look at, and 2 separate projects where the architects have given me permission to share the files with you. It was really nice of them to do it, but it'll just help you see that the things we're going to look at are pretty normal and pretty kind of average things. And these ones, I mean, what I'm showing you for most part are kind of above and beyond, but sometimes it's just nice to take a look and know what the point of all this is. So the architectural ones are there as well, so that you can kind of compare them to the structural ones. So these are just kind of shorthand things for what we're going to talk about. This is what an open web steel joist looks like, because we talk about them an awful lot. I'm going to go way more in depth in this later. We only have 2 hours, and I'm already pushing the limits. It's really easy to kind of push you guys over your 2 hours when you're watching a video, and I want to be careful that I don't kind of blow your exhaustion levels by providing too much data for you guys. Here's just what some hatching looks like. So that means when we have something, how we fill it in, how we color it in. Again, normally I don't even show these things to this class, but it's a big component of my graduate course, and I had to produce those all for this week anyway, and I thought you guys might really just like to see them. So again, these are available on Quarkus. I show a steel building, the same steel building and the same concrete building, with the same plan, doing the same things, but designed as steel and designed as concrete. So this is the basement for the steel plan. The light notes are things that are just interesting things for you guys to understand what's happening. And the black notes give you information, but are also the kind of notes we would normally see on a set of structural drawings as well. Here is not the ground floor, so I will go back and update that as well. So color for tributary areas and ground floor steel slide. So these will all be updated as soon as I repost the lecture for you guys. So if you're seeing the wrong thing, if you're seeing exactly what I'm seeing, it's because you need to go download the updated thing. It has no impact on what we're talking about, so just go download that when you get the opportunity. Here is a second floor version of the second floor of that steel plan. Ultimately, I will have cross sections of these buildings and typical details or details cut of this building, so you just have a bit more information to see what's normal. You can see here I've written what the loads are and even what the assemblies of these different floor systems are, so you can kind of see the nomenclature of what's normal here. CA, this is a column above, so this big beam right here that's spanning from this column to this column has a column up above it, which means it looks like the building is smaller above. This would probably be a girder. We'd call this bad boy a girder because it is picking up purlins and a beam and a transfer column. So it's doing a lot of heavy lifting, and we'd call it a girder. These ones here look like they're just picking up our deck that spans in that direction, so we'd probably call them purlins. This beam right here looks like it's just picking up purlins or open web steel joists, so I'd probably call it just a regular rolled beam. Again, that's going to matter when we start to talk about our sizing guidelines in a few weeks. Here's the roof plan of the building, a column schedule. Look, you can see these 3 columns right here stop at the second floor. So those were those columns above that we had. And here's some beam schedules that just show you what the beam sizes are. These are going to be handy because what we're going to do is we're going to look at some of these beams and we're going to do sizing guidelines, and we're going to do final design. So we can compare how the sizing guidelines compare to the final design. And what's handy is we already have a final design here so that we can cross-check our work with. Here's the concrete building for the foundation, the ground floor plan, the second floor plan with beams and drop panels, and the upper floor. These might be handy to go back and reference when we look at our concrete component. We're going to spend 2 weeks talking about steel explicitly, 2 weeks talking about wood explicitly, and 2 weeks talking about concrete explicitly. I don't have a wood building in this system because the wood members would be a different type of wood than we normally talk about. They'd be mass timber, and what we're going to talk about is mostly residential framing. We're going to touch on mass timber. But we're mostly going to talk about residential framing, and this building would be too big to build in that style. Ultimately, my hope is to have a simple basic building of a wood one as well for you guys to reference. There's also typical details, or the standard way things go together. If you're just curious, I think there's 130 different typical details that you can look at using different construction systems. So those would be ones that we would put at the beginning of a project that we might not even draw a detail for because they're so standard the contractor should know them. But just in case, here's something that you can take a peek at that might help you out. Here are the drawings that the architects were so willing to allow us to share the architectural ones with you, and I've also provided the structural drawings that I've done. What's interesting is this cube loft was done twice. We did the building in steel, and it went out for tender in 2008, and the week it went out for tender, there was an explosion in the steel market where, not literally an explosion, but China was buying up a lot of steel, and we had a huge shortage here. And thank you for lunch. we had a huge shortage here and steel prices doubled. It stayed doubled for about 2.5 months, but that was right when they tendered it in steel, and the owner said, this is ridiculous, why would you have done this? This clearly should have been a concrete building. Go back and build us a concrete building. So we went back and built a concrete building, or designed a concrete building. By the time we actually got to retender it, it was a year later, and steel prices had come down, and ultimately the steel building would have been the cheaper building. But by this point, they had already started foundation construction on the building, so it was kind of locked in as a concrete building there. But that's where a weird blip in the market can have really dire consequences on construction and the construction industry. So today was a long lecture with a lot of information, but not a lot of real kind of calculation work in it. So remember, you should know that live load is based on the building and roof type and how to look it up. You should be able to look up what the dead loads are and add them up for an assembly if somebody tells you what those are. You should know that wind, seismic, and snow are based on statistic probability, and you should probably be able to calculate the snow load one. You should know that soil, temperature, pre-stress, and vibration are other load types that exist, and ones that we consider. Often we realize that they don't govern, but we do have to stop and consider them for our building. That we have loads with combinations and importance factors and how to calculate those. That tributary area determines the total load on our object. That it can be different for different objects, and it can be even different for different loads on an object. And you should have a general idea of what structural drawings look like. So there's a lot to take away here. I think your assignment and quiz are pretty easy. There is fill in the blank, but like I said, I have been so explicit in what you need to write. You have to do a calculation, but I have given you the exact terms of how to write it in. It's up to you to figure out what those numbers are, but I've told you how to write them in. So I'm not going to take any kind of allowance in fill in the blank problems on this one. So next week, we're going to start into kind of some more interesting stuff. This was laying the groundwork for us. So feel free to download all those downloads I've given you, and in about an hour, go back and upload or download the updated presentation, which has those 2 or 3 slides that I'm going to fix for you guys. Okay, guys, have a good week.